turn the temperature up in the room or something like that. I'm interested in decisions and communications of potentially great significance and consequence, where paradoxically we most want to accept this form of communication to allow people to have more autonomy, and at the same time the risk of error is so much greater. So we'll talk about the 3 examples and then conclude with what can one do about this to make sure the hope is that this technology will go forward and be helpful. So to design to meet the needs of communicators and interlocutors. And I put a little, it's probably a little bit hard for you to see, but that this is like a screenshot of an article published in the New England Journal of Medicine commenting on a recent paper, which I'll come to in a moment. And the title is Freedom of Speech, and this is being published by scientists who are identifying in particular the social and human rights significance of these developments, right there in the title. Okay, so starting with the technologies, this field of augmentative and alternative communication has been around for decades, and there's a whole range of different forms of technology able to assist people. There's a lot of text here, but there's great variety at the level of tools, symbols, selection, and prediction components. So let me be a bit more clear. The kinds of tools that you see in AAC include books of images that people can point at, for example, spelling boards, image boards, speech generation devices, devices to convert into written or typed output. The symbols that are manipulated by people include photos, pictures, letters, words, phrases, sometimes gestures are made. There's always a way of selecting the communicative symbols that are being used, and this includes motion of specific body parts, use of pointers, mice, computer mice, eye tracking to see where someone is looking in order to select, for example, letters. Switch access scanning involves playing a stream of elements to someone, and then rather than having them to have to select something from that is static, they just make some sort of movement when the element they want has been presented. I don't know if any of you have read The Diving Bell and the Butterfly, involving a man with locked-in syndrome who dictated the whole book by blinking when he got to each letter. And someone was able to translate what he was intending with this very slow and difficult method of communication. And of course, this prediction element, we're all familiar with autocorrect on the phone, which is, it seems to me, about 90% of the time saying something silly. For example, I teach a neuroethics course, and it routinely changes my communications to neurotics course. So I now know to look out for that after having invited people to my neurotics course. So when we think about neurotechnologies, we are doing the same sort of thing, but rather than relying on some small bit of preserved movement that the person has, because notice that all of these AAC depend upon some movement or gesture that the person can make. And what if they can't do that? There's locked-in syndrome, there's a range of things that might impede their ability to move at all, or in the case of the diving bell and butterfly, even the preserved movement is very small, and so it only allows access to a relatively slow and tedious method of communication. So what's exciting about these neurotechnologies is we're looking for mental activities. And these can be manipulation of attention. People can give or refrain from giving attention, and that can be detected. Now, here's where it gets pretty interesting. So the science is now, with lots of heavy data processing and machine learning, able to extract and interpret the representation of movement in the motor cortex of the brain. And so to find out what the neural correlate or representation of a hand movement is, and detect and interpret handwriting, and also imagine speech. And that works the same way. It is a representation of the movement of the vocal tract that is then decoded and turned into the phonemes, the sounds, and turned into speech, or written output, turned into communication. So these devices can work from the scalp with electroencephalography, from the brain surface, which picks up a lot more information, although obviously is not ready for prime time use involving brain surgery. The outputs are variable. And again, there's an element of prediction to try to speed up the decoding. So a lot of the research involves constrained communication space where there is, within the model, there's some sense of what is likely to follow each letter or each word rather. There's a guessing going on as well. And so this becomes important when we think about how much more we rely on these devices. We have a rather non-transparent system of prediction and probabilistic decoding. Are we getting that right? On the other hand, it sure speeds up the device to have this kind of structure. Okay, so I'll tell you about two of the recent pieces of research. This first one, 2021 is the one that the little editorial was talking about. This involved the detection of imagined speech in a 36-year-old man with anarthria, so inability to articulate speech due to brainstem stroke. And they implanted sensor in sensory motor cortex. I'm not a neuroscientist, but I understand this somewhere up here, so that's why I have a hand on the head. And they reported 22 hours of activity while he tried to say words from a set of 50 words. So that's a lot of data, 22 hours. And machine learning then was then set to the job of figuring out what each phoneme, what the representation of his vocal tract looked like as he imagined. He's not speaking here, he's imagining speech. And using this model then, they use a natural language model to try to estimate probabilities of each word based on the one that came before. And it wasn't too bad. Obviously, this is early days, but all things start a little bit kind of rough like this and improve. So pretty exciting, I would say, for people who are completely locked in and unable to communicate at all with their environment. Now, to me, this gets really interesting. When I was reading about this, I thought, great, here's a whole other field I need for my 10th life that I need to do everything that I want to do in my life. But neurolinguistics, fascinating, trying to figure out the models of speech production. And there's a whole bunch of different models. It's relatively poorly understood how we communicate. But a lot of them involve this sort of sequential or modular approach. Sorry, let me open a parenthesis and say, we know from brain of the aphasias that follow different kinds of brain damage that the production of speech involves all kinds of different areas in the brain because there's such a strange mixture of aphasias of people who can express but cannot perceive, who can do some aspects of speech but not others. So anyway, close parenthesis. So basically we have this sort of sequence in which some sort of concept is formed. At some point that's linked to the semantic word. And at some point we have to, in our brain, create a model of what the phonemes, what the phonological what phonological elements are present in the word. And then we have to actually get a motor representation of producing that phonological element, the phoneme. And so in theory, one could start to try to pick up different parts of this communicative chain, perhaps to get around different kinds of aphasias that knock out one or the other segment. So I confess I'm not a neurolinguistic linguist, and so I don't know if that is possible, but it's extremely exciting, I think, to start thinking about what we can learn about the production of communication, but also what other strategies could be adopted to try to help people who are not locked in, but who have stroke, for example. And so the next study, which I have to admit, my head nearly exploded when I read this one. This was extremely exciting to me. This is 2023 last winter, and this is a very different approach. So we're not trying to get motor representation of sound, of speech. Instead, we're going directly to semantic content, the meaning element, divorced from the movement to produce sound. So this approach, it was published, as I said, last year. And what they did was they took 3 subjects and they put them in the magnetic resonance imaging imager and did functional magnetic resonance imaging, which picks up patterns of blood flow in the brain, which is interpreted as signifying activity in that part of the brain to get a pattern of brain activity. And so they had these people listen to 16 hours of recorded speech, various podcasts, which I notice are some of my favorites. So anyway, so these poor people lay there for 16 hours listening while their brain is being imaged. And in addition, they actually showed these people videos, silent videos, and imaged their brain at the same time, to see whether in fact this semantic content could be detected across modes, the auditory and the visual. And so they found, in fact, yes, this kind of more or less works. Again, it's still not perfect. Again, it's well above chance, but again, it's a proof of concept really about where things can go. And so